Shabazz, thank you so much for the kind introduction and also the kind invitation to be here with you today to speak at this wonderful unveiling of Equinox after so many hours of engineering and innovation. A very good evening to all of you. I'm Catherine Tsiopoulos. Details are up there on the slide. I'd also like to thank our hosts for acknowledging, for their acknowledgement of country, and I'd also like to acknowledge the people of the Wurrung and Boonwurrung language groups on whose, of the Eastern Kulin Nations, on whose unceded lands we conduct the business of the university, and I pay my respects to their elders past, present and emerging, and any First Nations people that are with us today. I'm always very grateful to be at an event like this that celebrates the depth of talent that we have within our student cohort here at RMIT. It is so wonderful to see this talent on show and in front of so many of you here in the audience. To the students, we're so lucky to have you here at RMIT University. I hope we've been able to help you to better understand your talents and bring them to life. And this is an exemplar today of how applying your talents can achieve great things. A university motto is a skilled hand and a cultivated mind, and that reflects our commitment to improving the lives and futures of people in a fast-changing society. I can't think of a more appropriate sector that motto represents more than space, which is the truest test of humanity's ambition to reach for greatness beyond our Earth. So much goes on into developing such a most incremental moments of progress, and each discovery like this creates the possibility of so much more, not just in the field of space, but also right across science. Here at RMIT, we are committed to enhancing the life and work through stimulating high-quality education experiences and pathways. It's embedded in our strategy to 2031. We have a strategy called Knowledge with Action, and Direction 1 is Learning Through Life and Work. Our student experience aims to be connected, our students aim to be connected across RMIT's distinctive open learning ecosystem powered by expert educators who challenge and inspire. So here's a call out to the educators, all of the academic staff, leaders and researchers that support our student cohorts. So the learning that we have here at RMIT is active, authentic and applied, and it's delivered through a holistic blend of on-campus, online and work-based learning. To the RMIT Rover team, you perfectly demonstrate this lofty ambition. Made up of talented, ambitious and innovative students, you undertake work that's far beyond the scope of many more seasoned professionals. Recently, the team showcased 2 Rover-focused capstones at an engineering showcase, Engenius 2025, and I was thrilled to attend that amazing showcase expo full of budding students and industry and excitement from the students that I talked to on the day of how much that they were impacting the industries that they were working in for their capstones, and the pride that they had in their innovations. And there was quite a bit of the equipment, one that I was about to drive on, ride on and drive off, and they said, "Oh man, this is a prototype, not meant to be taken away," but amazing. And here today we'll see amazing work. I also want to thank you, huge thank you, Associate Professor Ben Cheng, for your supervision of both projects and supporting our students throughout their journey. Of course, well done to the students that have been working with you. Earlier this year, the team also completed the Australian Rover Challenge 2025, placing 8th nationally and 11th overall. Quite an amazing achievement. Held at the University of Adelaide, the team put their rover, RAT Mark II, to the test in a series of challenging tasks, pushing the limits of their engineering, teamwork and problem-solving skills. To be recognised at this level is such a testament to the talent and hard work that each member of the team has put into this and to their studies, and it's certainly inspiring. The talent, dedication and excellence shown by RMIT's space projects goes beyond our student cohort as well. It's well known that RMIT University is playing a key role in designing and building what could be Australia's first lunar rover. The Rover prototype was unveiled last year, and the Australian Space Agency and Minister for Science, Tim Ayres, announced its first mission at RMIT's Advanced Manufacturing Precinct in August this year. For our university to be playing an important role in the creation and implementation of such groundbreaking project in Australian space history fills me with a lot of pride. And I was there at that launch, and certainly to be profiled, the students primarily, their mentors and supervisors for a project that's going to land us in space is just amazing. It also showcases how at RMIT we work with partners to be with industry and governments or non-NGOs, non-government organisations across our region, making an impact and championing an inclusive and sustainable society. That really speaks to our DNA at RMIT. Technology university, hands-on and industry-focused. Probably, that's where that's what we're known for. Outside looking in, RMIT is industry-focused. An exemplar that we are celebrating today of that, exactly. So in reaching for the stars, what industry could better capture the shared journey of humankind as we continue to push the frontiers of understanding our own place in the universe? So whether you're a hobbyist, an engineering student, an industry professional, the family of our wonderful students, or you're just curious about what goes on into a building of a lunar rover, tonight is your chance to go behind the scenes and meet the minds that have built rovers at RMIT, and this one here. So I'm excited to find out a bit more about our talented teams of academics and students, and I look forward to what we can all achieve here at RMIT in the coming years. Thank you very much, and I look forward to the unveiling. Thank you.
Thank you very much, Catherine. Of course, as Catherine mentioned, at the end of the day, a lot of this does come down to the supervision we get from academics. I'd like to introduce our academic supervisor, Professor Ben Cheng, to say a few words as well.
Okay. First of all, distinguished guests, Catherine, Jennifer, and also Daniel, thank you so much for coming. And also thank you all the fantastic student team member, your friends, family, thank you so much for joining this wonderful event tonight. I'm Dr. Ben Cheng. I wear different hats, but tonight I'm wearing the hat of the academic supervisor of the team. And that's one of the many fantastic roles that I have at RMIT, and I enjoyed every second of it. It all started in 2019, when one day, two students knocked on my door saying that, well, Ben, we would like to start a rover team. At that time, I still haven't listened clearly enough. I thought that, oh, they're doing something with the Range Rover. That's great. Let's do that. So, as people know me, well, that you know that I say yes to a lot of things, and definitely this one I say yes again. And later on, I know that, oh, this is about space rover, which is cooler, even better. This is one of the many yes I say, and this is the very few that I didn't regret after all. I really enjoy every moment of spending time with all of you guys. Right, so I need to say something about the team, so this is what I'm going to say next. Building the rover is with more than just nuts and bolts and code, and it is more about building a team. In the School of Engineering and also STEM College, Catherine, since you're here, I'm going to say that slogan, our slogan again. We do have a slogan in STEM, is in STEM we care. The word care got 4 characters, and these 4 characters are representing 4 very important attributes that we all value. They are collaboration, accountability, and then respect, and finally empowerment. I don't see that slogan simply as some wordings on the wall in the team. I see our team, executing it every day in every of their action. Let me tell you a little bit more. First, start with collaboration. And within the team, needless to say, majority of them would be from School of Engineering, but we do have a large population of them are from the School of Science, Computing Technology. We also have students from School of Design and also Business. They are running different part of the rover, for example, writing the code to do the automation and doing the science module. And later on, they will tell you more about that. So I'm not going to, give you a spoiler. So this is a very good demonstration of how collaboration could happen in a good way, and how interdisciplinary collaboration can lead to very amazing results. Second, then we have accountability. When we say accountability, I think we often translate to safety, and we treat safety as our #1 priority in the team. And here, at this moment, I would like to take this moment to acknowledge all the effort and help provided by our technical staff and also professional surveys. Because of them, we can go through all the risk assessment, spending endless number of days and nights doing that, and making sure that while our students are doing a lot of breakthrough, okay, they can come home safe. That is very important, and may I have a round of applause to all the technical service staff that provided all the support to us. Thank you so much. And the next we have, let's see, respect. Right? That is the thing that I'm most proud of. In our team, we treat inclusive very important, and we highly emphasize them in all our recruitment and also in the appointment of our leadership role in the team. And for that, I would like to, again, praise all the members in the HR sector of our team. You guys are doing a very good job. You make our team a better team every day. And finally is about empowerment. Needless to say, the goal of what we are doing is to set up a student-led team for them to design the rover, fabricate the rover, and also driving the rover to compete in different national and international competition. I often joke around saying that, well, in the team, I'm the least important person. I'm not just joking, because this is your team, and you have done a very good job. Thank you so much, everyone. Thank you. Enjoy the rest of your night. Thank you.
Thank you very much, Ben, for your kind and encouraging words. Up next, I'd like to invite Daniel Ricardo to the stage to give us some insight into Arch.
Let's see. Maybe. Do I need to point it somewhere? Oh. I pressed the right button, right? Oh, there we go. Cool. All right. I need to look back to the slides. But hello, everyone. And people up there. Hello. I didn't even see you there. I'm Daniel Ricardo. I'm one of the organisers for the Australian Rover Challenge, which is one of the competitions that are open to students. It is the main competition within Australia. And today I'll be talking a little bit quickly about what is the Australian Rover Challenge, what are we doing it, why are we doing it, and what are we planning for the future. So I'm here on behalf of an organising committee. So there are 3 other individuals that make up the judging committee on behalf of the University of Adelaide. So I'd just like to acknowledge that although I'm here speaking today, I'm part of a larger team that works really, really hard to offer the Rover Challenge as an opportunity for you to compete and all the Australian teams to come and compete against each other with these amazing rovers. So for those who aren't too familiar about what it is that the rover gets sent off to Adelaide to go and do, the Australian Rover Challenge is a robotics competition for undergraduate students within Australia. And it's held over at the Roseworthy campus in South Australia. So this is a dedicated facility built purposely for the Australian Rover Challenge and some other robotics activities at the University of Adelaide. And it allows us to make a full-scale lunar surface environment where we can do missions like the Australian Rover Challenge, which is a 4-day event, so Thursday to Sunday. We have different scenarios that the teams compete in as part of an end-to-end lunar surface mission. So this is really unique in the sense that there aren't that many other competitions focusing on the moon specifically, and it's giving undergraduate students opportunities in participating in full-scale missions that are equivalent to what NASA and ESA would be doing as part of research. So the Rover Challenge is broken up into written deliverables. So as part of a systems engineering role, you would write a critical design review and a system acceptance review. And this is giving students the opportunity to practice if you were to go into a job as a systems engineer or any role within a mission, you would take a role as part of writing these deliverables. And then there's also the 4 tasks. 4 tasks, 100 points each, and that gives you the overall score about how we rank the teams as part of the Rover Challenge. So a big question that I like to sort of ask the audience and to think about is like, why are we doing the Rover Challenge? Like, why did we make it? And one of the core reasons is increasing STEM engagement. So it wasn't that long ago that the Space Agency was actually started in Australia, and they set out a roadmap about what it is they're going to do in the first 10 years. And one of the pillars was growing the Australian workforce so that there is an industry within Australia, but the only way to get there is to get more students involved in STEM and interested within this space ecosystem. So to address one of those points, we started the Rover Challenge to give students a platform, an opportunity to actually pursue a career within space. The other thing is that it is the Australian Rover Challenge. So prior to when we made it just after COVID in 2021, or 2020, sorry, there weren't any Rover Challenge opportunities within Australia. The only one was the main one, the University Rover Challenge in America, in Utah. So you have to pack up your rover in suitcases, go through American customs security, drive out to Utah, and then set up in the middle of nowhere to compete in a 4-day event. The financial burden in order to attend that competition is extremely high, and the universities aren't able to support all students in accommodation, transport, registration fees, food, so students had to pay for themselves. That shouldn't be a scenario in any competition that allows students to participate. So one of the main reasons was breaking down that barrier so that Australian students can participate in a full-scale mission within Australia. So you don't have to worry about the international fees, shipping the rover overseas, you can just ship it domestically. And this is one of the examples of the University Rover Challenge. So I helped start the Nova Rover team when I did my undergrad at Monash, and there's me, down on the bottom left. This was the first year we competed. So back in 2018, this was the first time an Australian team went to America. Amazing opportunity. It's cascaded. It's completely changed my career path, as well as a lot of the other students that participated in the Rover Challenge. But the main thing was that we were only able to do that because we could afford to do it. And ever since I graduated, that really hung in my mind of that shouldn't be a barrier that exists, a financial barrier to participation. So that was one of the main reasons why we made the Rover Challenge, is to, 1, increase STEM engagement, 2, reduce financial barriers, and 3, make sure that all Australian students have the opportunity to participate and follow the same career paths that we're now following down. And I guess the main one is you're at university to get a job. So the Rover Challenge is a premier opportunity where industry partners can attend and see the best of the best within Australia showcasing what it is that they do. So it's not, here's a CV, it's there is my CV. And it's unique in that the sense that the industry can act as judges and get hands-on experience with students. So not only can you engage with the industry, but you can ask them questions. You can ask them what it's like to work at the company, what it is that they're looking for, and then showcase what it is that you could provide with hands-on experience. And here's an example of one of the judges from Boeing interacting with some students. So it's not just students going to the Rover Challenge, competing and going home. It's an opportunity for you to talk to industry, learn about what it is that if you are interested in a career path, actually engage with that person, which is kind of rare. Like, you don't really get to do that overseas, at least my experience when I went to the University Rover Challenge. And if you are an industry partner, you'll get hands-on experience. So there's Eric from Caterpillar, who's the head of autonomy within the whole Caterpillar business, and he's sort of digging out samples for the Space Resources task. So what have we achieved so far? One of the things I like to look at is how many teams we have and where are those teams from. So when we first started, there were 3 teams, all within Australia, and we had about 120 participants. So that was already a huge milestone and a great achievement. We went from just one team at one university, suddenly to 3 teams with over 120 students attending, not just those also part of the team who couldn't attend for various reasons. 2022, we scale up again. More Australian teams, more participants. 2023, we had our first Polish team. I don't know what it is in the water in Poland, but they have some incredible university teams all building incredible rovers. So we had our first international participant from Poland, and I believe they won that year. 2024, we had our next international participant from Bangladesh. And last year was probably our biggest year yet, and we had teams from all over the world. We had over 300 participants attending, and we had several teams who registered who didn't make it through the CDR, SAR milestones or couldn't attend for various other technical reasons. So one of the other things that I like to showcase as well is, unlike the other Rover Challenge, we treat it sort of like a spectator sport, like AFL, where you can watch it on live stream. So this is one of the other big things, that it's not just attending and seeing it in person, it's, hey mum, dad, check out this YouTube video, here's our rover traversing down a ramp and participating in a lunar mission. So some stats is we reached over 6,500 people from around the world, which is incredible, and each year that number grows steadily. So what are we planning for the future? So there's lots of growth over the last 5 years, which is incredible, and it really warms my heart whenever I get invited to come speak at these opportunities, is that the scale of how many students are now participating in these opportunities, and I'm really looking forward to where you all end up in the next few years and growing that future career workforce. So next year, we've had a huge amount of new teams domestically and overseas registering as part of the CDR. So one of the other things as well is that we've had between 500 to 1,000. I say that's a very big band because I don't actually know how many members there are in every team, because each year there's just more and more students getting involved. But the key thing I want to point out there is it's 500 to 1,000 individuals. Like individual people with their own passions and dreams participating in these opportunities and getting the opportunity to participate in this growing national challenge. The other thing that we've introduced this year, and it's good and bad depending if you've part of the team, is we're introducing efficiency multipliers. So it's not just to design and build a system, because if we say it can weigh up to 70 kilos, every team's like, cool, let's make it 70 kilos. Space is a function of mass, power, consumption, and size. The more heavy something is, the larger it is, the more it costs to send it to space, and the more power consumes, the less likely it is to do more science in a mission. So we're trying to challenge the students on the teams to think about real-world design challenges. It's not just designing a system based on the maximum limits imposed by us, it's how can we optimize? How can we improve the system? I was speaking to some students on the tables about how you managed to reduce the heat consumption of the rover by 70%, power consumption, size, mass. It's incredible. It's awesome. That's exactly the things we will have to do when you do progress into a job after the Rover Challenge. One of the other things that I take great pride in is the Rover Challenge isn't just a competition that you attend and you compete against other teams and you form a rivalry. It's an opportunity to collaborate and communicate. And one of the key things is that we foster great inter-team communication. So if you do get the opportunity to attend, you'll notice that all the teams are in one big workshop. That's awesome, because in the past, one team may have broken a piece of their chassis, or they needed something 3D printed, and another team stepped in, loaned them a part, 3D printed them something. And that essence of teamwork is a great opportunity to meet people from other universities who you may be working with in the future. Some things we do to incentivize that is after the competition, we do a tug of war where the rovers get tied against a rope and we see which team can rip the other one over. And we also do things like best team culture, most interactive team, best new performing team, most improved team, and the trophies. So when we first started the competition, we didn't have a lot of money, so we said, okay, teams can bring all the failed parts that they made during the development of their rover. We spray painted them gold, and we let the teams make their own trophies. Now that's really symbolic, because I like to think that the Rover Challenge is in the sense of a rising tide lifts all ships. Every mistake that one team makes, you get to share that mistake with other teams, and as a collaborative community, you're learning from each other and you're progressing each other forward. You're always pushing each other further and further. So those trophies are symbolic of, although you may win, you're standing on the shoulders of the rest of your team and all the people who came before you. And the most important rule that we like to say as judges is have fun, because you don't get a lot of years at university, you don't get to experience this a lot of the time, where you have complete freedom of what you can design. You have the opportunity to work with large teams, interact with teams from all over Australia. So make sure you take the most of this opportunity and have fun. So here's some photos from the trophy building from 2 years ago. And we do have nice trophies. It's not just spray painted gold, failed 3D printed wheels and blown Raspberry Pis and MOSFETs. There's the tug of war from 4 years ago. There's a victim from Swinburne post tug of war. Some of the other things is that it's hard to convey just how difficult it is to build a rover, but then operate it under simulated competition conditions. So the soil is extremely loose, just like the moon. It is extremely difficult to simply drive, to get all those different subsystems working in a functional individual system. So the fact that a team is moving, if you ever watch the live stream, the fact that a team moves off the start gate and does a task represents so many achievements beyond just something that performs 100% of every task. So I really want to commend, no matter what it is that you get to do, simply moving is a huge achievement. There's also digging. So if you are interested in the Rover Challenge, there's a lot of information. I don't have enough time to dig into it as much as I would like, but doing all of the tasks, digging, resource extraction, autonomy, interacting with the robotic arm, there's so many things and aspects that we give opportunities for the teams to explore, and whatever it is you're interested in within space systems, you get to explore that and perform at a global stage. So here's one autonomous rover finding a waypoint. The other thing is that for the international participants, we actually have Australian animals come into the competition, and it's one way to interact with the Australian environment, and it provides a good opportunity for teams visiting from overseas to experience what it is like in Australia. So there's the Polish team interacting with one of the lizards and a crocodile. One of the key things that I'd like to highlight as well is this year we had one team who participated really well in berm construction go overseas to NASA and participate in the NASA lunar robotics competition. So that's their equivalent of digging and moving on the moon under a full-scale simulated environment within a big test facility with lunar simulant. Next year, we'll be opening up qualifiers as part of University of Adelaide's official big crater facility. So this is a dedicated large shed with high-fidelity regular simulant where teams will, after competing in the Rover Challenge, be able to compete in a simulated NASA lunar robotics qualifier where the winning team will be able to go compete in NASA lunar robotics again next year. So just something to be aware of. Thank you very much.
Thank you very much for the insights, Daniel. Of course, the team is multidisciplinary, and the wide range of challenges that we need to do at the Australian Rover Challenge definitely require all those disciplines. So, to give everyone a clearer picture of who we are and how we operate as a team, the RMIT Rover team is a student-led engineering group that came together in 2019 with the goal of representing RMIT at the Australian Rover Challenge, as Dan mentioned. Since then, we've grown into a multidisciplinary team with over 80 members dedicated to designing and building autonomous rovers. This year, our team is structured across 3 tiers of management. At the top is the team lead position, supported by 2 wings, systems engineering and operations. Between that, we have 4 technical subsystems, mechanical, payloads, electrical, and software, each responsible for a different portion of the rover's main platform. To take you deeper into how all of these parts come together, I'd now like to invite Kaylin Granger, our systems engineering lead, to explain how we manage all this.
Hello everyone, my name is Kaylin and I am the lead of systems engineering and integrations within the Rover team. We are a rather large crew with 4 primary engineering subsystems, mechanical, electrical, payloads and software, and an even more formidable project scope. As such, the role of systems engineering within the team is to coordinate and facilitate the communication of engineering to systems across the subsystems to ensure a unified and cohesive solution to all the competition requirements. This involves establishing well-defined system interfaces within the rover to ensure that all components integrate seamlessly and problems are both identified and addressed early in the design process. Additionally, a large part of this includes determining requirements for the competition milestones to achieve minimum viable product and functional readiness. At the core of our design cycle is the INCOS V model for systems development, as recommended by the NASA Systems Engineering Handbook. We closely follow this industry standard model as it enables step-by-step development whilst catering to the extended lead times of component purchase and manufacture. It ensures that at each stage of the project's development is verified against initial requirements and that all required functionality has been met. Our design cycle for the 2026 Australian Rover Challenge officially began with a team-wide post-competition debrief. The performance of the previous RAT2 rover was across both competition and design implementation was carefully analysed to highlight key areas of improvement for Equinox 1. Here we identified potential platform-wide changes, such as transitioning to a 4-wheel design for better traction and manoeuvrability, exploring a more modern replacement for the core notoriously difficult and unreliable Jetson computer, and experimenting with lighter and stronger carbon fibre components with the help of the RMIT Composites Lab and technical staff. With these changes in mind, we began designing and prototyping a new rover over the last 2 semesters with the goal of achieving minimum viable product in anticipation of the release of the new competition rules in September. During this stage of development, key interfaces between engineering subsystems, such as software to payloads and electrical to software, were defined to ensure that all components fit together upon completion of the project. With a critical design review competition deliverable being completed, we are now at the point of adding the finishing touches and verifying our design's competency for ARCH 2026. Finally, integrations within the team primarily operates field training. Unlike previous iterations, we have been fortunate to have a fully functional older rover solely dedicated to academic research projects such as capstones and training needs. Minor modifications were made to the 2024 RAT2 to mimic the new interfaces present within Equinox. This provides an ideal verification platform for systems integration in which payloads and software systems are tested on a weekly basis and operators can build their experience and functional flaws can be identified well in advance of development deadlines. The opportunity to see what shakes loose gathers vital information in verifying the design. We are pretty much broken 90% of the components on the rover at some point or another, much to the amusement and despair of my colleagues. Several melted gearboxes or burnt electronic boards highlight what needs to be adjusted as the design progresses. We have also been fortunate to have the support of the vocational education staff and facilities within Bundoora, allowing us to test our rover in the massive indoor sandpit and even building competition props such as a landing platform during their classes. This enables an easy transition to the new rover when it is ready and with hardware and training conditions having a direct parity to the configuration for the 2026 competition. I would now like to invite Summer and Venkata from Operations.
Good evening, everyone. My name is Summer, and I'm the operations lead for the RMIT Rover team.
And I'm Venkata, the Deputy Operations Lead. Together we oversee the non-technical side of the team, the side that keeps everything moving behind the scenes while our brilliant engineers build the rovers you see tonight.
As Venkata mentioned, operations supports most of the non-technical aspects of the team, such as business liaison, personal management, marketing and social media, events and logistics, branding and merchandising, and increasingly, outreach and community engagement. This year, our subsystem has grown rapidly, and we went from a fluctuating 2 to 4 members to a humble team of 11 dedicated people, and more members to come next year. None of what RMIT Rover does would be possible without the support of our generous sponsors. This year, we're proudly supported by partners across multiple tiers: RMIT University, Robert Harness, ANSYS, Leap Australia, Life Saving First Aid, PTC, Altium, Keyshot, ODrive, and iFixit.
Your contribution empowers us with software, hardware, tools, and specialized knowledge, all essential in building a rover capable of competing on a national stage. Thank you for believing in student talent. Now I'd like to introduce Aidan West, our team member, to discuss our team events.
Hello everyone, I'm Aidan, and as part of HR in our team, we've seen the introduction of about 40 new active members this year. And with that comes a great new sense of community. So firstly, we had, thank you, induction days for all our new members to get introduced to their subsystems and people. Then we had our safety days to introduce them to the many risks across the whole entire lab and rover. Finally, we have a lot of full team meetings which help us collaborate and troubleshoot many of our interesting problems. To keep morale high, and our communication and social events often include things like the Red Bull Run for Life, our games nights, wings nights, girls nights, and many team lunches. So thank you all for coming. Now I'm off.
Thank you, Aidan. This year we've made a deliberate push to expand our outreach and give back to the community. Through collaboration with the Sir Lawrence Wackett Defence and Aerospace Centre, we helped host the Young Women in Aerospace and Defence workshops, one in July and one in September, where we guided middle and high school girls through Python programming, constructing mini rovers, and catting on Onshape. Their enthusiasm and curiosity were incredible and reminded us of why we do what we do.
We also visited RMIT's Introduction to Engineering course, where we connected with hundreds of first-year students building their own rover concepts. We showcased our 2025 rover, conceptual CAD models, and an AR preview of our upcoming 2026 rover. And we're proud to say that many of those students who attended their lecture, including myself, are now on the team.
During National Careers Week, we also visited Kew High School, bringing our rover prototypes and a payload to run an extended Q&A with the students. It was inspiring to see their interest in robotics and engineering pathways.
Industry engagement remained a priority as well. Earlier this year, we attended CSIT's Industry Night to share our work and build relationships with RMIT's computer science and IT community. And just last month, we attended Leap Australia's Tech Day, a major event with over 200 attendees, giving us a chance to connect with industry professionals and other student teams across Melbourne. Looking ahead to 2026, we're gearing up for some major improvements to how the rover team presents itself and operates behind the scenes. This includes a new team website, updated team uniforms, full logistic plannings for Arch 2026, more media content, more events and collaborations, both internal and other student teams, and most importantly, deepening our relationships with sponsors and industry, ensuring long-term partnerships and supporting our growing technical ambitions. 2026 will be a huge year, and we are excited to build a culture that we can grow with the rest of the team.
We want to thank members of the operations subsystem for everything they do behind the scenes. Your work is often invisible, but never unnoticed. Tonight wouldn't be happening without your hard work. Now we'll be passing on the mic back to Shabazz to introduce our 2026 rover, Equinox.
Finally time. All right. Our previous rover, RAT2, gave us a pretty strong foundation to work off of, but it also showed us where we could grow. Equinox builds on those lessons as we refine, reimagine, and get ready for the next competition. Before we dive into the technical side of things, I'm honored to reveal our brand new rover. Can I get a drum roll, please? Equinox! Now, I promise everyone will get the chance to come up and have a look at this, but moving on to the more technical part of the night, I'd like to welcome our fantastic mechanical leads, Shalisha and Priyal, to the stage.
Good evening, I'm Jalisha and this is my co-lead Priyal, and I'll take you through what Mechanical has done this year, why we made those choices and how the team has grown with us. Our subsystem provides the rover's load-bearing structure, suspension interfaces and mounting for power and payload systems. Early on we realised the fastest path forward wasn't just more prototypes, it was a smarter cycle, defining load cases, running simulations early, documenting our decisions and signing off before changing our geometry. That gave us the confidence to try these ambitious ideas. One of the biggest wins from this discipline was the chassis. Our design changes weren't trendy, they were responses to repeated failures and new rules being introduced. We reworked the entire rover structure.
Apart from the M5 screws.
A smaller aluminium space frame paired with the structural carbon fiber panels. The change brought about a 57% mass reduction on the chassis itself, and it helped us explore composites and fabrics, which in turn introduced new skills and manufacturing capability to the team.
So how did we make the rover move? Regarding suspension, drivetrain, and wheels. For drivetrain, we deep dived into motor and gearbox pairings. We designed pivot into a modular sealed unit. We relied heavily on 3D printing early to nail geometry and interfaces before we sourced these gearboxes and motors. On the drive modules, we prioritized maintainability. Candidates were bench test under continuous load monitoring, and pivot redesign concentrates on bearing placement and sealing so the rover survived the dusty arena. Suspension also evolved in parallel. We introduced a four-wheel rocker layout with composite differential bar and aluminium uprights that reduced the upspring mass and improved articulation when paired with the new pivot. Wheels and tires were one of our favorite problems. Our current wheels display aluminium spokes for repairability and TPU tires for predictable compliance and traction tuning. We're hoping to start wear and traction trials to finalize and compound before integration. We introduced a lot of importance into design meets proof, such as verification, manufacturing, and experiments to let us innovate. Finite element analysis was explored early on to lock in geometry and safety margins. These results then went straight into material compatibility and optimization of said parts. The simulations really helped us understand where parts would fail without committing these resources. We tightened the manufacturing processes with proper inductions, composite layups, improved tolerances. Our big challenge, however, was repeatability. So we developed workshops. In short, upskilling our members was on the forefront. We also finalized a research task, giving team members ownership to scope investigations, then translate findings to real prototypes. And that's how we've explored multiple projects like the mini rover, cable-driven differential, different wheels, mast and pivot variants, and the ability to manufacture, of course, our own composites, to name a few.
This focus on upskilling paid off as the team has a better understanding on how projects and prototypes come to life. Some headline gains we've measured have been 55% of the overall body weight reduction, 57% of the chassis mass reduction, 75% weight reduction on our differential bar, a 15% wheel weight reduction, and a 35% volume reduction compared to our RAT2. Those numbers show we're not just making changes for the sake of it, but we're delivering measurable improvements that make the Rover lighter, tougher, and easier to service. Being part of Mechanical has been a journey that shaped our skills and who we are. We relied on each other a lot, and that support made it easier. Leading this team taught us how to teach, training recruits, documenting decisions, and building confidence so new members can contribute meaningfully.
As the first duo female mechanical leads on this team, this journey has had tough moments. But to all the women out there in engineering, we see you, we're proud of you and how far you've come, and we hope that our journey helps inspire the next iterations of this team. Again, a huge thank you to every single mechanical member for all the work. All of this would not have been possible without you, and with days in the lab, Intel Security literally had to kick us out. So if you're curious about anything that we've mentioned, please come say hi. Thank you.
I would now like to invite all the members of Payloads that are presenting to come to the stage.
Hello everyone, I'm Andrew, the Payload Systems lead. Payload Systems is a new subsystem responsible for constructing all the rover's payloads that let it complete mission tasks and earn challenge points. It includes the development of a robotic arm, science module, excavator, and pavers. I'm joined by David, the Deputy Payloads lead, Hetty, Tralisha, and Shristi to help present all our hard work. We'll start off by showing you our redesigned arm developed for use in the post-landing task. We began this year with a focus on building an arm that lets us deliver outstanding precision, strength, and reliability. Last year, the biggest challenges we faced were accurately handling the hose connector and performing delicate tasks like button pressing. To address this, we redesigned the end effector, upgraded the actuation system, and improved the arm's architecture for better control, precision, and performance.
Previously, in our old arm design, we used linear actuators in our second and third joint. However, after some extensive research and development, we found that off-the-shelf strain wave and planetary brushless actuators provide the best outcome given the requirements for the competition and the short development time available. The actuators would allow us to handle significantly higher torque in a more compact package, and allow the arm to handle up to 20 kilograms of load at full strength, at full extension. While this is a bit overkill for the Australian Rover Challenge, for now anyway, this extra torque will allow the team to compete in future international challenges, such as the ones in Canada or Turkey, which require these heavier loads. The implementation of these new actuators has also the added benefit of reducing backlash, which is what limited our precision last year. They result in smoother, more controlled motion system, which is essential for competition tasks. We have also improved the arm by redesigning its structure and simplifying the joints, while retaining the carbon fiber rods to create a lightweight yet strong and robust frame. This allows for maximum weight efficiency while supporting all required operational loads. With all of our implementations, the arm can now fold in a securely stowed position, greatly improving the volume efficiency during transport and mobility. We've taken a big step forward, and we're excited to see how we'll perform. And now on to space resources.
The Space Resources task tests our rover's ability to find and extract useful materials on the Moon. Space exploration is highly resource intensive, and extracting resources in situ is the most cost-effective way to enable extended visits to the lunar habitat. Our Space Resources payload uses detection equipment to examine sites and quantify the concentrations of water and ilmenite in regolith. We can then choose the sample that has the highest water content and extract pure water from the sand.
For detection this year, we've taken a really exciting step forward, reintroducing our new Raman spectroscopy module, which gives us the quantitative information about the sample by analyzing how it scatters light. From that, we can estimate water content more precisely and identify minerals like ilmenite. This lets us pinpoint the highest value sample set before we start drilling. We also use both a green laser at 520 nanometers and a red laser at 670 nanometers as part of the spectroscopy setup. Using two wavelengths help improve clarity and reliability of our readings.
We combine this system with microscopy, which gives us qualitative details such as grain shape, texture, layering, and visual cues that help us understand the sample's structure. Microscopy also helps identify ilmenite visually, and it acts as a validation tool whenever the spectroscopy results look borderline or unusual. By pairing quantitative spectroscopy with qualitative microscopic insight, we end up with a much more balanced and reliable detection system. We get precise data, visual confirmation, and we dramatically reduce the chance of choosing a low-value sample.
In 2024, we made it our goal to extract an icy regolith sample and process the water all on board the rover. In 2025, we did this for the first time. Following from this success, our material extraction system uses a sheathed auger to feed regolith into an extraction chamber where an evaporation condensation process separates water from the sand. Our aim for the 2026 competition was to improve material and water extraction efficiency, resulting in more pure processed water. To achieve this, we are introducing ceramic heating rods to the chamber, allowing the system to heat to 160 degrees within a minute. With the removal of the fan from the condensation chamber, we more accurately simulate what processing would be like on the moon. Material extraction is improved with a retractable sheath to maximize material being funneled up the auger, as well as a new carbide Forstner bit to break through the hard, icy regolith. By improving previous successful designs, we create a model that is more efficient and can extract more water. Finally, we'd love to show you our fully redesigned excavator and pavers.
The excavation and construction tasks test our rover's ability to clear terrain and complete construction on a lunar surface. This requires lifting heavy payloads, transporting large volumes of sand, and deploying dust-mitigating pavers that improve mobility on the moon. To achieve this, we continued with the traditional front-loader excavator system, using two linear actuators for bucket lift and tilt, but with some significant improvements. Firstly, the new bent aluminium frame reduces overall volume and allows better placement of the lift actuator. Our previous excavator pulled the frame at a shallow 20-degree angle, wasting much of the applied force by transferring it into the frame itself. Our new design pushes upward at a 45-degree angle, doubling the effective lifting force and reducing power demand. Finally, we increased bucket volume from 5.2 to 18.3 litres. That's a massive 337% increase that allows our excavator to move more regolith per trip. The result is a more effective excavator that carries more material faster while using less power.
Our pavers will use a lightweight composite design with a strong Nomex honeycomb core, giving them high rigidity without the extra weight. They will deploy quickly using a simple and reliable hook-lock system, making them easy to deploy and durable.
Working in payload systems offers a unique hands-on engineering experience. Team members develop practical mechanical design skills tailored to our in-house manufacturing capabilities, including 3D printing, machining, welding, waterjet cutting, and more. They also build strong integration skills, combining mechanical, electrical, and software elements to create a functional mechatronic system. At its core, the Australian Rover Challenge makes us engineer solutions to real-world problems. The tasks mirror the challenges of modern space exploration, whether it's extracting resources with our science module or conducting maintenance tasks with the arm. all while operating under strict mass and power limits. Working in payload systems teaches us to balance ambition with feasibility, making decisions that transform bold ideas into simple working solutions. Thank you to all our members for all your hard work. And while some of our parts are still in the manufacturing process, please check out our stall at the end of the presentation. Thank you. I'll now pass on to our electrical leads, Cody and Vicky.
Good evening, everyone. I'm Yucher, also go by Cody. I'm the electrical lead, here to talk about the electrical subsystem, or the drive subsystem, or the power and communication subsystem. We go by many names. One of them is also the nerdiest subsystem. At the end of the day, we make sure power is delivered to all peripherals of the rover, and also making sure the battery doesn't explode, of course. Beyond that, we also handle all communications within and out of the rover, from the radio interface down to the CAN bus that lets different devices talk to each other. Building on top of our electrical success last year, the electrical system on Equinox comes with a major redesign, fixing many issues such as wiring bloats, cable overheating, reliability, assembly simplicity, and more to be discussed. Shown above is our electrical hierarchy, and let me walk you through it, starting with the most significant change, the move to 50 volts, achieved by connecting both our battery packs in series. Well, it's more like 44 volts more nominally, but 50 volts sounds friendlier. I can immediately see some people gaping, a little bit worried, but don't worry, because this change means smaller cables, better thermal performance, and reduced weight, a change Mechanical surely enjoys. I'll hand it over to Vicky to showcase some more projects.
Hi everyone, I'm Vicky, the electrical deputy lead. Now, with that battery upgrade, a lot of this year's projects are focused on accommodating that power, and by extension, improving the safety of the rover. Beyond adjusting to just the new competition rules, we also recognize the increased risk of moving to a higher operating voltage. In fact, the first thing that's connected to the battery is the in-house battery management system, which can remotely monitor each individual cell. And in line with the batteries is the power monitor, which displays the live power consumption data. And improving on RAT2, the emergency stop system has received a shiny green partner, acting as the official start button alongside to the red e-stop button. In addition, our new RGB LED strips provide visual feedback on the rover status, meeting the updated competition requirements. Our power distribution boards have also been updated to handle that 50-volt input. The first of which is the buckboard converter, which interfaces step-down converters to offer 2 channels of adjustable voltage outputs. There's also the switchboards, which mainly deliver power to the drive system that provide us 8 channels of individually controlled 50-volt outputs. Each of these boards provide live power monitoring. And another custom PCB is the inertial measurement unit, or the IMU, from which we can extract orientation and motion data. And it's powered by a Pi Pico 2. This also allows us to use the extra I/O pins to drive additional power to low power systems.
Now, you may wonder, none of these devices have built-in CAN support, for which I introduced the RAT CAN on the left over there. The name paying homage to RAT Knob 2, our previous rover. RAT CAN is a SPI to CAN translation layer for the microcontrollers that do not support it natively. Now, to hook all these CAN devices up, hear me out on this, we found out that using star topology, while uncommon, is viable in our use case. We are actually using a CAN bus hub to connect all these devices together, and that will provide a benefit of simplifying the wiring process, and it also improves reliability. And speaking of reliability, thermal issues were actually very rampant last year. The benefactor of that turned out to be the motor drivers. Hence, on Equinox, they have been exiled of the main chassis. If you look on the left over here, you can actually see them right next to the vertical uprights. They're actually the black boxes over there. Being the main heat source, aside from the South Australian sun, spreading them away from the main electrical system has given us significant thermal performance and better system reliability, with the additional benefit of improved switching control performance.
Just give it a minute. All right, so after dealing with RAT1 and RAT2's cable management, we really wanted to avoid dealing with that mess that's just essentially spaghetti bolognese with a bit of 20 volt sprinkled throughout. Hence, in our next move, we implemented both high power and low power backplanes. This is a massive improvement over the old bus bar system. It's safer, it's cleaner, it's more standardized, and it makes cable management infinitely easier when it comes to debugging. And as for communication, we're still comfortably using the Ubiquiti radios, capable of 400 megabytes per second point-to-point connection via an omnidirectional antenna on the Equinox and a sector antenna at the base station. That about sums up it on a surface level. So what did all of this work accumulate into? Well, we generated 70% less heat, we reduced cable mass by 40%, and our electrical system within the main chassis is 33% smaller compared to RAT2.
Now, beyond the technical achievements, I'm incredibly proud of how our team has grown. The electrical subsystem have all upskilled themselves through dedicated training sessions covering PCB design, soldering, cable manufacturing, CAD skills, and most importantly, battery handling. Workflow around the lab has also gotten a lot more efficient through use of inventory tracking, project tracking, and of course, documentation. We would like to acknowledge the hard work of everyone within our electrical subsystem. Kudos to you all sitting amongst the audience. As for our welcome guests, if you want a closer look at any of our boards, I invite you to our booth from which we'll be showcasing what all of electrical has worked on. Thank you. I'll hand it over to software to discuss command and autonomy.
Ooh, can I see everyone? Yes, I can. All right. Hello, everyone. My name is Mi. I am one of the software leads. Today, I'll be talking to you about the primary responsibility of our subsystem, including how we interface with electrical and payloads. This year, our focus is on three things: strengthening the control stack, tightening the software-hardware interface, and making our entire development process more reliable. Software is essentially the nervous system of the whole rover. And our job is to ensure that every piece of hardware, be it actuators, sensors, communicate reliably to construct the control logic that brings a rover to life. One of the biggest upgrades this year was building a modular O-drive control library. It supports multiple operating modes, for example, the traction control, which give the rover better grip and reduce the wheel slip. We also implement the electrical stability control, also known as the ESC, for the yaw regulations. So when the rover drifts away from its command heading, the ESC will use a PID controller to automatically correct the wheel commands and pull the rover back on course. These systems are modular by design, which means they're also easy to test in isolation, swap out, extend, and they run cleanly with the rest of the control stack. Because of this modularity, we are able to build a much stronger testing unit, dummy situation, simulation functions for all of these. With ROS2, the middleware that coordinates our nodes and message, we could trace how low-level motor commands travel up through higher-level logic that gave us early visibility into integration issues and made debugging much easier. This year, payloads integration also got a big upgrade. We standardized how our payloads communicate over ROS2 and our custom CAN bus library. This made it easier for us to test the payloads independently and swap components without breaking the whole system. For science payload, we're planning to train an AI-based detection system for measuring the ilmenite and water percentage in the sand samples. For the arm, we have moved fully into the MOVEit and ROS2 planning pipeline. Finally, we put a lot of effort into cleaning up the operator experience. The camera feeds now run over WebRTC, which dropped latency significantly and made our stream much more stable. We also redesigned the GUI operator so they can view everything at a glance, whether it be payloads control, electrical telemetry, wheel state, science sensor, temperature, speed, and more of that. The result is a more smoother remote driving experience and a far more reliable view of the rover during field testing. And with that, I'll hand over to Hassan, who will take you through the autonomy and some of the research direction we've been heading.
Hey everyone, I'm Hassan. I am the other software lead and I take care of the rover's autonomous decision-making processes. Autonomy this year was built around a simulation-first approach. Our autonomous system is fully ROS2 based with Gazebo simulator integration to verify system design before conducting real-life tests. Our autonomous stack is mostly complete. However, one of the most pressing problems we all face, which I believe most roboticists here would agree with me on, is the problem of robot localization, where the rover asks itself, where in the world am I? With our autonomy payload, which houses our sensor suite that consists of a depth camera, a LiDAR, and the Jetson computer, it helps us tackle these localization issues by allowing independent testing from the rover's drivetrain. We have also included a GPS module to measure system accuracy against ground truth data. Aside from the ongoing engineering projects, we also undertake numerous research projects. One of our ongoing projects is a robotic exploration framework, which is built on top of the ROS navigation stack, also called NAV2. It selects the next best place to go in the world based on customizable heuristics and passes it onto the NAV2 stack. It's plug and play, letting us experiment with different algorithms. Here in the screen, you can see one of the more prettier algorithms. It's tree-based. It's called Rapidly Exploring Random Trees. It's beautiful, isn't she? We are also exploring agentic navigation. I think all of us here have heard about AI agents, starting with cloning behaviors from human operators and the current control stack. Even though these projects are not meant to be a part of the Australian Rover Challenge, our aim is to foster a culture of research in the team that allows us to contribute to not just space robotics, but the spectrum of robotics as a whole. If you're interested in learning more about these projects and the autonomy payload, please feel free to visit our booth and ask us questions. We love that. A lot of this was tough. We had shifting embedded libraries, changes to hardware and interfaces that needed rewriting more than once. We got through it by running tight iterative tests and working closely with electrical to pin down bugs. Traction control and electronic stability control were not drop-in features either. We had to tune parameters, log behavior, validate in simulation, validate on the rover, and do it over and over again. But the final performance boost really made it worth it. One thing that I'm proud of this year is how much the team has upskilled. We treated modeling the rover as an exercise in ROS. For those interested in autonomy, it became a stepping stone to the higher level systems. We ran hands-on simulations before letting people touch hardware, and we really pushed hard on documentation so that onboarding was smoother and knowledge transfer actually stuck. We also added a continuous integration pipeline along with a Dockerized environment so people can work on the code from anywhere in the world, which is a huge quality of life improvement. This year wasn't just about new features. It was about building a cleaner, more modular and maintainable software stack and building a team that was stronger and more capable than when we started. Thank you to everyone in software for all the hours that you put in, and to electrical, mechanical, and payloads for working us through the hardware. Thank you all very much. I'll now hand it over to Shiv and Felicity.
All right. Thank you all for being here tonight and celebrating such a proud moment with the RMIT Rover team. We'd like to give a huge thank you to our sponsors, industry partners, academic staff, volunteers, alumni and mentors. Your support has shaped every step of this journey. Equinox represents a year of learning, teamwork and persistence. We've grown so much as engineers and as a team, and we're incredibly proud of what we've built together.
We are heading into the Australian Rover Challenge with big ambition and real confidence in what this rover can do. Before we wrap up, we'd love for you to stick around, come take a closer look at Equinox, chat with our leads and enjoy some refreshments, which I've been told are almost ready. And you're more than welcome to connect with our partners and community as well. I look forward to chatting with some of you. Now, on behalf of the team, thank you again for your support. Equinox shows what we can achieve when we work together. And we can't wait to show you what's next. Enjoy the rest of your evening. Thank you, everyone. Could we please move a little bit to the left? Oh, sorry, to your
as well. Tell them that as well. Oh, fuck yeah, go.
But who's going to pack?
Wait, can you ask? Yeah. Do you want it?
What were you saying?
I got it. Hello everyone. Just letting you know that we are going to have to leave the premises in like 7 minutes. So we have a reservation at the Oxford Scholar for the after party for 9:45 p.m. I believe, but we can start heading down now. Why are you taking a picture of this? This guy.
Oh no, it's...
Anyway, yeah, so if we can start thinking about clearing out now, that would be great. And for whoever's coming to the after party, I will see you there. Was it bad back there? Could you not hear anything? Nothing.
Is this yours?
Everyone, missing phone, if anyone's curious, or if it's yours, I don't know. Hannah? Okay, where is she?
that's